All right, let me start out here by just pointing out as clearly as possible that the material in this small video can be treated as optional. Okay, it deals with manifestations of tunneling, which is discussed somewhat in your book, and which really is just kind of for me, a very curious and interesting topic. And so since there is mention of some of these things in the textbook, I thought it would be worthwhile to go ahead and record at least a brief conversation about them. So here goes. So tunneling involves the passage or transmission of a quantum mechanical particle through an energy barrier. When we talk about an energy barrier, all we mean is some region of relatively higher potential energy that's relative to its neighboring places. And so in the picture here, for example, I've got low potential energy over here, and then this is my barrier because it's a range where I have relatively high potential energy, right? And so under certain circumstances, we could have a wave function pass from one side of that barrier to the other without actually going over the top of it, all right? An example of that, one that I'll mention briefly right at the end of this video, is the situation in something known as an Esaki or tunnel diode, which exists where you have two regions of conducting material with just a gap between them, right? That gap traditionally should be an insulator. We would not expect to be able to pass a current across there. And so that also constitutes an energy barrier, right? If I'm trying to get an electron to hop between those two pieces of conductive material, then there's going to be some energy barrier associated with that. To think about tunneling, we have to think about what happens to the wave function as it approaches and interacts with an energy barrier. Okay, just like when at the end of the last video, I talked briefly about what would happen if the walls in the particle in a box were of finite height rather than being of infinitely high potential energy. In this case, if our wave function is approaching the barrier from one side, we want to think about what happens before it gets to the barrier, what happens while it is in the barrier, and then what might or might not be able to emerge on the far side of the barrier. Okay, to find solutions for this, you'd again, the particle as it approaches the barrier should be a free particle, like our free electron problem, and it should start off with a wave function like the ones we saw there. We can think about the boundary conditions that happen when we're at the edges of the barrier, specifically the fact that the wave function and its derivative both need to be continuous as the particle or the wave function transitions from one region to the other. Okay, and those arguments together will cooperate to give us a description of what's going to happen. Again, we're not going to work through the details of the math here. We're just going to look at qualitatively what would happen. So this is a kind of schematic representation of what's happening. If I look on the slide there, we've got a wave which is approaching the barrier. The barrier is represented by the green region. The wave initially, as the large amplitude drawn in that pinkish purplish color, approaches the barrier from the left-hand side of the screen. Okay. So think of those bars as just representing the oscillations in the wave, because if this is a free particle, then its wave function, we wrote those, we said we could describe those essentially as sine and cosine functions, right? When it hits the barrier, it turns out the wave function will have two possibilities. One is that it could be reflected. It could act like we would expect for a classical system and essentially just bounce off of the barrier. Right. The second is that just like the wave function from the particle in a finite box or a box with finite wall height had some penetration of the wave function into the wall. In this case, our wave function could begin to penetrate into our barrier, right? And that's what's represented here. And notice that the wave function decays. Its amplitude is going down as it moves in the barrier. Right, so there's a cost associated with moving in that higher energy space. Right, depending on how thick the barrier is, if the barrier is sufficiently narrow, then it's possible that our wave function, if the wave function still has amplitude when it gets to the far side of the barrier, represented over here, then what will happen is that the wave function will emerge on the far side. We will have what's labeled there as the transmitted wave, which means that the wave function has actually tunneled or passed its way through that barrier, right? This is something that, again, a classical system can't do. You can't throw a ball at the wall and every once in a while just have it go through, right? We know that you'd have to have enough energy to actually penetrate or destroy the wall for that to happen. In this case, the amplitude of our wave function never has, actually goes over the top of the barrier. It is in fact passing through it. And that's where the word tunneling comes from, because it tunnels through that barrier. So the wave function would look like this. Remember, this situation in here, this is qualitatively similar to what happened, I had the sketch in the last video for the case where the particle in the box had finite walls, right? When the wave function is within the barrier, its amplitude is going to decay. It's going to decay exponentially with penetration into the barrier. Right, so here my barrier is drawn now. It's got a width L, similar to what we did for the particle in the box. Okay, if when I get to the far side, if the wave function has not made it down to 0, it looks like if I just sort of eyeball the midpoint there, 0 is somewhere right around where I drew that line, right? So somewhere like that. Looks like I'm probably a little low there. The first try was better, but then I will have a wave function with diminished amplitude emerging on the far side. Okay, but this does say now my particle still exists over here. It has gotten out of this confined region by finding its way through the barrier. Okay. What is this good for? Is it good for anything? It's true that initially this was kind of just a mathematical curiosity of interest to people that were deeply into doing quantum mechanics. There now are a variety of things that can be explained this way for natural phenomena, or that can be engineered in a way to take advantage of this behavior. And one of those is the scanning tunneling microscope. The word tunneling in the name refers to the fact that it's based on the tunneling of electrons. Okay, some of you may be familiar with the STM in its use in materials science, things like that. It's extremely good for the imaging of surfaces, right? It's often true for atoms right on the surface of a solid that the arrangement of those atoms in the top layer or the top couple layers is often at least slightly different than the arrangement of the atoms down in the bulk. Okay, I might have mentioned that when we talked about diffraction a little bit, I think. That's just because the atoms at the surface don't have any nearest neighbors, and so sometimes their positions will shift because of that. All right. The STM provides a technique that really does look at and produce more or less direct images of the atoms in that top layer. Okay, and so how does it work? The STM relies on being able to produce a tip, which is essentially a wire with a very, very, very fine point. Ideally, you want a wire where the tip, the point, comes out to end up being essentially a single atom at its apex. Okay. The pictures down here in the corner, these are electron microscope images of a tip, and you can see that this is, the length scale here is 50 microns, as it says down here in the corner, and the point is obviously a whole lot smaller than that, right? People that do this, they cut these tips from just pieces of wire, and there's a little bit of art and a little bit of luck to it. Oftentimes they have to cut a number of tips, and some of them work really well and some of them don't, okay? That tip is mounted so that it is suspended above the surface we want to image. There are devices here that let the tip be moved around in X, Y, and Z directions. If you're really interested in the technology of this, like it says up here, those are generally piezoelectric devices. That's a technology where you have a crystal of a solid material which has a somewhat strange symmetry property that means that that material will expand or contract as you apply a voltage to it in a controlled way. Those are used because they can move that tip in very, very small increments, things that are, you know, like on the nanometer and sub-nanometer scale, which is going to be important if we're trying to look at individual atoms. Sorry, I moved the mouse and skipped ahead there, okay. Here we have our surface represented by the green atoms here, and D over here, that just represents the distance between the atom at the surface and the height of my tip, say. Okay, the barrier in this case is just the space or the gap that exists here between the tip and the surface atoms, right? Simplest case, assume the surface is a metal, right? So I've got a conducting surface down here. My tip is a metal, so I've got a conducting material there. In between, I've got, in most cases, just air. In some cases, I might have the whole thing in a vacuum system, but in either case, I have this space there where the electrons should not be able to pass, right? In this case, the thickness of that barrier is going to depend on a couple of things. It's going to depend on, number one, the vertical distance of my tip away from the surface. That means that if my surface looks like the one here, where this is a side view, in the places where the top atoms are sticking up higher, my barrier thickness is going to be smaller, right? So I might expect to see more tunneling there because the wall it has to tunnel through is going to be smaller, right? In places where the tip is over a valley in the surface atom is effectively further away and I might see less tunneling. All right. The other thing is I could just move the tip up and down again to control such things. Okay, and so there's a little bit of just some electronics loops here and things that do this. Obviously, it relies on a lot of elaborate engineering of how this thing works. But what happens in the end is if you measure a voltage or a current over here, you control one of those and measure the other, and those parameters will depend on what is the separation between the tip and the atom at the surface. So if I take this device and I scan it so that it moves across the surface as it goes from being above a mountain on the surface where an atom is sticking up to a valley where the atom is recessed, I'll see differences in the amount of current that flows, right? It's that current or voltage reading that is then used to produce the image. When you see pictures of STM images, they're just image processed representations of what happens in these scans. I put this next slide. This is one of a large number of pictures of things having to do or having been made with STMs and imaged with STMs. Right? This one is usually referred to as the quantum Corral. It's kind of a really peculiar and interesting thing made, I believe, by some people that worked for IBM at the time. And they had a lot of interest in studying this as a way to manipulate surfaces and atoms, and did some of the earliest work as this once this technique or this STM was invented. Okay. In here, the mountains in that, the peaks in that thing that make the circle around there, each one of those peaks there represents an iron atom. And so the fact that it looks like a mountain is just because those iron atoms have been deposited on an otherwise smoother surface. They are sitting on the surface of a copper crystal, okay? And the atoms have been put there to be arranged into that circular pattern using an STM. It turns out you can also, by changing the voltage on that tip, you can use the tip to pick up an atom and actually attach it to the tip, move it to where you want to, and then change the voltage to deposit the atom back down. Okay, so the investigators here have deliberately set up this circular ring of iron atoms. It says in the description over there, there's 48 of them, right? The ripples, the wave distribution inside the ring actually represents the wave function of an electron that is trapped inside of there. Okay, it is a more or less direct representation of the wave function of an electron, which in this case is trapped in that circular ring, right? It's a bit like our particle in a two-dimensional box case, except now the box is circular, which means the wave functions for it look like the standing waves in a drum head. Okay, if you took a round drum head and hit it in the center, you'd get a wave pattern that looked more or less like what is seen in there, and that's exactly what is being looked at here. Okay, and if you if you haven't seen them, most Gen Chem books have some of these pictures in there because they're part of the description of why we believe in atoms these days. There's a lot of things around where people have made various stick figures and other characters, representations of things, just because once you can pick up atoms and move them around, you can make all sorts of little designs with them. Okay, that's an STM. It has really revolutionized the study of surfaces because it's much easier to get information about what the arrangement of surface atoms is from looking at a picture like this, where the features we're seeing are in what is often referred to as real space, meaning where it looks like there's a bump. That's because an atom is poking up there, right? As opposed to diffraction patterns, which are often referred to as being in reciprocal space, because there's a transform between how the spacing in the dots in the diffraction pattern correlates with the spacing in the atoms themselves. The next couple are things that are just naturally occurring phenomena that are also explainable in terms of tunneling. One is the fusion of light nuclei. Okay, it turns out iron 56 is the most stable nuclide, and nuclei that are lighter than that can, at least in principle, fuse together to make heavier nuclei. Nuclei heavier than iron 56 tend to undergo fission and split into their pieces. Okay. These fusion reactions are very important in stars, for example, so they do take place, but they require, as the fact that they happen in stars suggests, they require very extreme conditions. Right? In general, that means the activation energy, activation barrier for such a reaction is enormously high. Right? It means, for example, as the simplest case says, take two hydrogen nuclei, two protons, and try and have them fuse so that they form a helium nucleus. Okay, if you were to do that, the first thing you're trying to do is take two positively charged particles and push them very close together, close enough that they can get to be in the same nucleus. As you might imagine, the charges do not like that as they approach one another, and so it's quite difficult to do. The diagram on the right there is a artist rendering of a machine called a tokamak, which is a proposed, not yet completed fusion reactor, this one to be in France. In these things, what happens is that that shape in the middle, in this part here, where you can see the passageway there and coming back out over there, this is a slice through, and that is what is called a toroidal shape. It kind of looks like a donut going around there, and the scheme would be that you got a plasma set up in there where you had ionized the hydrogen atoms that were present, and that plasma is typically then magnetically suspended so that it doesn't interact with the walls, because the energies that have to be sustained in there are so high that they can't be actually in contact with things. These reactions actually turn out to happen by a tunneling process where there is, on the other side of things, if I get my nuclei very close together, my two protons very close together, then they move into a region where there's an attractive force between them, where they actually do go lower in energy by forming the combined nucleus, right? The reaction is exothermic to get to that side, but the activation barrier is very, very high, right? And so what happens is, if this represents a wave function for the proton, it has to pass through this barrier. So in order to do that, it needs a lot of kinetic energy. It needs to get up high enough that it's in a region where the barrier is not as thick, and then it can make it to the other side. If the wave function emerges here, then it can fall down into this potential well where the two protons are then allowed to stick together. A similar thing actually happens in proton transfer reactions in water and aqueous solutions. It turns out that in an acidic solution, for example, the acidic protons tend to hop from one water molecule to another. Okay, that process also is not really energetically viable by any sort of normal means, right? Meaning the energy available is not sufficient to actually tear the proton off of one molecule, have the proton then just diffuse through the solution or whatever and encounter another water molecule. Right. What happens here again is that if this height in the middle represents the activation barrier, this is a wave function associated with the proton being on one water molecule. This is a wave function associated with it being on another water molecule. If those wave functions can overlap in here in the activation barrier, then the proton can tunnel through that barrier, right? In this case, it's a proton doing the tunneling, which is obviously a little bit more difficult because protons are a lot heavier heavier than electrons, but the same thing happens, and this has been fairly definitively proven to be how these proton transfer processes actually take place. You can prove that by doing things like comparing having a proton versus a deuteron, where that would be a heavy hydrogen, right? A hydrogen with a neutron going through there. And if you compare those rates, you can predict based on the way the tunneling works, what should be the ratio of the rates, and that in fact works really well. The last one in my quick survey of examples here is something that's it's really a wild idea. It is what is known as a tunnel diode, which is an electrical component which actually exists. You can build circuits that have these in them. And to do this, like the picture that was there near the beginning of the video, what you want is you want two pieces of semiconductor, both appropriately doped, and you want them to be very, very close together, but there is a gap in between, right? That gap is now going to be on the order of nanometers. So there is a barrier, but the barrier is not very thick, right? As the picture shows here, the graph here is a plot of current flowing across the diode versus the voltage, right? And in general, what you expect is that the slope of that current versus voltage figure should be positive, right? Meaning as I increase the voltage, I should expect to have more current flow. And indeed, initially I do. I get this region here where that's definitely happening. Eventually, though, I get to a voltage where something really crazy happens and my curve turns and bends downward, okay? To see exactly how crazy that is, go back and look at Ohm's law over here, right? Ohm's law is just starts off as V equals IR. If you rearrange that, you can convince yourself pretty easily that di dv, which should be the slope of this plot, is equal to 1 over r, where r is the resistance, right? That means when the slope goes negative in the part represented by the red piece of the graph, that means this device is acting like it has a negative electrical resistance, right? That's not supposed to happen, obviously, in normal circumstances. And as you might imagine, if you're clever at designing circuits, you can do a lot of things that otherwise would be inaccessible if you can generate a component that, when you want it to, acts like it has negative resistance, right? And there are some applications of these things that have been constructed that actually take advantage of that behavior. Right, that wraps up just a quick tour of some ideas about tunneling. I'm fine if you haven't, if some people haven't chosen to watch this one. My expectation, based on the times I've taught the class, is that there are a number of you who are just kind of curious about strange technological possibilities and things like that, who may have found this interesting, and I hope you did. Thanks.